Hello everybody, and welcome to the top of page 138 in the workbook. And on this page, we are going to kind of do a lead-in to one of the major results in this section that we would like to talk about. So first, just a little motivation here. In all of the examples that we've done up to this point, we've been talking about orthogonal sets of vectors, and we discovered that having an orthogonal set of vectors allows us to calculate linear combinations in a very special way, in a way that's much more computationally efficient than the old way in the case of a large problem. Okay, and to be able to do that, it's very much in our interest to be able to find an orthogonal set of vectors. Okay, that's what we need in order to use that technique for finding those coefficients. Okay, so let's read this general problem together here. So we'll suppose that we're in an inner product space V, and we're going to start with a linearly independent set of vectors. All we know about those vectors is that they're linearly independent. What we'd like to do is to find an orthogonal set, S prime, of vectors that spans the same vector space. Okay, so kind of what this is about is starting with just a general linearly independent set and replacing it with a set of vectors that's orthogonal and spans the same space as the original set. Okay, how do we do that? Well, it turns out we can do that in a very systematic, step-by-step way. Okay, we'll figure out how to construct the first vector, then the second vector, and just so on down the line using kind of an inductive process here. Okay, and we'll start by just letting v1, the first vector in this set S prime that we're creating, we'll let it be w1. Think of that as like a basis step, just a starting point. And then we could ask the question, how would we come up with the second vector? How would we define the second vector in S prime so that it's orthogonal to the first vector? Okay, well, here we can use a picture to motivate ourselves a little bit. Okay, so I'm going to draw a representation of W1 and W2, the two vectors in S, the first two vectors in S. Okay, we'll assume that we're in R2 just to make the picture simple. Okay, so maybe this is W1 and this is W2. They're probably not orthogonal to each other. Okay, they're linearly independent, but probably not orthogonal. Maybe make the observation that we define V1 to be the same vector as W1, and then we want to ask the question, how might we calculate V2 so that it's orthogonal to V1? Okay, well, one way is to make use of vector projections. Okay, if we take this vector W2 that we have here and project it onto W1, okay, we'd come up with this vector right here. And notice from the picture that if we do that, okay, let me just make it clear by drawing in a right angle there. Okay, let's try that again. Okay, so the point that I want to emphasize here is that this should be a right angle. Okay, there's our projection. And my point that I'm trying to make here is that this vector is a good choice for V2 because it's orthogonal to V1. Okay, and the question is, how would we calculate that vector? Well, first thing to maybe notice is that the projection that we have down here, that's going to be a scalar multiple of V1. We don't know what the scalar is at the moment, so I'm just going to call it A times V1. And from the picture, what we can see then, just using ordinary vector addition, AV1 plus V2, those are like two sides of a right triangle. That has to add up to W2. Okay, if we take that equation, we can solve it for V2. V2 is going to look like W2 minus AV1. And here's the thing. We already played this game when we proved the Cauchy-Schwarz inequality. And if you look back at that proof, we actually found a value for that constant A. Okay, I'm going to remind you of what that was. Okay, from that proof, we know that A is the inner product of W2 with V1 over the length of V1 squared. Okay, so what that means then is if we kind of substitute that value of a in, we get W2 minus the inner product of W2 with V1 over the length of V1 squared times V1. Okay, turns out we make that definition for V2, we've got a vector that's orthogonal to V1. Okay, so far so good. The first two vectors in this set that we're building are orthogonal to each other. Okay, it turns out we can continue this process inductively. Okay, we can get a definition for V3 that looks like this. W3 minus inner product of W3 with V1 over the length of V1 squared times V1 minus the inner product of W3 with V2 over the length of V2 squared times V2. Okay, now here, I'm kind of pulling that out of the air. I'm asking you to trust me that that's the natural inductive continuation of what we did. Okay, so just to reassure ourselves, if that definition makes sense, then V3 should really be orthogonal to V2 and V1, both of them, because we're trying to build a set S prime where all of the vectors are mutually orthogonal. So we could do just a quick double check here, just see if that's the case. Okay, so is V3 orthogonal to both V1 and V2? Let's see. Okay, now to make the computation a little bit nicer to write down, I'm going to give these two coefficients names. I'm going to call the first one B1 and this one B2. All right, so when we check, is V3 orthogonal to V1, we would need to take the inner product of V3 with V1, and we're hoping that it's equal to 0. Okay, so our definition of V3 was given on this line. It looked like W3 minus B1 V1 minus B2 V2. Remember that how we defined the B1 and the B2 above. Okay, we're going to take the inner product of that with V1, and then we'll use the linearity to pull this apart into three inner products. So the inner product of W3 with V1 minus B1 times the inner product of V1 with itself minus B2 times the inner product of V2 with V1. We're just using linearity there. Okay, let's make a couple of observations about this. Okay, starting with the inner product of V2 with V1, we were careful to define V2 so that it's orthogonal to V1, which means that this has got to be 0. Okay, so that term goes away. All right, and then kind of continuing on here, doing a little bit more algebra. Let's rewrite this one more time. Okay, I'm going to go ahead and resubstitute in what B1 was. We gave it the name to be this ratio here. So W3, inner product of W3 with V1 over the length of V1 squared, but notice that the inner product of V1 with itself is the length of V1 squared. So look what happens here. Those two cancel, and what's left? Well, we're just taking the inner product of W3 with V1 and subtracting it, so we get 0. And that confirms that the two vectors that we started with, the V3 and the V1, are orthogonal. Okay, great. And I'll leave it to you to double check that if you took the inner product of V3 with V2, you could go through the same process that we did above and come up with 0. And so we've confirmed what we said up here, that V3 is orthogonal to both V1 and V2. Okay, so what we are describing here is a step-by-step process for building an orthogonal basis, and there's a name for it. This is called the Gram-Schmidt orthogonalization process. Okay, whoops, let's see if I can spell this morning. Okay, and we could also maybe say it continues inductively to produce an orthogonal set S prime. That's the whole point of this. Okay, and so at the very top of the next page, it summarizes all of this in one theorem, Theorem 6.4. Okay, so I'm going to scroll up. Okay, and I want to emphasize that Theorem 6.4 just generalizes everything that we said above. Okay, so we start with a linearly independent set, and we'd like to replace it with an orthogonal set that spans the same space. And we start with the same assumption, the basis step, and then this formula that you see here builds the vectors in S prime step by step. Vk looks like this, and that formula is the same formula that we started, the same process that we started in the example above. Okay, and so in future examples, we will actually use that and see how it works to actually build an orthogonal set.